Mass transfer in laminar flow. Many mass transfer operations involve diffusion in fluid in laminar flow. As a convective heat transfer in laminar flow, the calculation of such operation is amendable to well-defined theory. There are three common applications in mass transfer operation involving diffusion in fluid, which is first, a fluid falling as a film down a wall. The second one is a fluid flowing slowly along a horizontal flat plate. And the third one is a fluid flowing slowly through a circular tube. Where all of these applications, the mass transfer will occur respectively between a gas and a falling liquid film from the surface of the flat plate into the flowing fluid, and also from the inside surface of the tube into the flowing fluid. So right now we will discuss on falling lamina around liquid film by considering a thin liquid film containing A and non-volatile B, or sometimes we call it as stagnant B, falling in laminar flow at steady state down one side of a vertical surface and exposed to a pure gas A, which is the pure gas A will diffuses into the liquid as shown in the figure 3.12. Okay. The surface is infinitely wide in x direction, normal to the pitch, and flows in the downward direction, y direction. So the surface is infinitely wide in the x direction, which is the x direction, and then the flow is downward y direction, this one, and mass transfer of A in the z direction, and the mass transfer happen from this point to the left hand side. By assuming the rate of mass transfer of A into the liquid film is so small that the liquid velocity z, uz will be 0. And from fluid mechanics, in the absence of an effect of equation of motion for the liquid film in fully developed laminar flows in y direction will shows as in this equation, which is mu d square uy over dz square plus rho g is equals to 0. So by referring to that figure, which is mass transfer from a gas into a falling laminar fluid, we can say that when a fluid is flowing in laminar flow and a mass transfer by molecular diffusion is occurring, the equation is very similar to those heat transfer by conduction in laminar flow. These phenomena of heat and mass transfer are not always completely analogs, since in mass transfer several components may be diffusing. Also, the flux of mass perpendicular to the direction of the flow must be small so as not to distort the laminar velocity profile. In theory, it is not necessary to have experimental mass transfer coefficient for laminar flow, since the equation of momentum transfer for a diffusion can be solved. But however, in many actual cases, it is difficult to describe mathematically the laminar flow for geometry such as the flows past a cylinder or in a backpack. So the experimental mass transfer coefficient are often obtained and correlated. A simplified theoretical derivation will be given for two cases of laminar flow. So one of it is mass transfer in laminar flow in tube, and the second one is the mass transfer from into a falling laminar flow laminar liquid film. Okay, so based from this diagram, we can say that we will consider the mass of solute A into laminar falling film. Okay, which is important in wet wall column. So let's say this is the wet wall column. In developing theories to explain mass transfer in stagnant pocket of fluid and is turbulent in turbulent mass transfer, the solute A in the gas is absorbed at the interface, then diffuses distance through into the liquid so that it is not penetrate in a whole distance. So we can say that Z is equals to del at the wall. At steady state, the inlet concentration, which is state as Ca, is equals to 0 at this moment. Okay, at point Z, from the inlet concentration profile of Ca, which is shown in this figure. Usually, fully developed flow where uy is independent of the distance y is established quickly. If del is the film thickness and the boundary condition are uy is equals to 0 and z is equals to del, meaning that z is equals to del, meaning that no slip at the solid surface. And whenever duy over dz is equals to 0 and at z is equals to 0, meaning there is no drag at gas liquid interface, which is shown in equation 3.88. It is readily integrated to give a parabolic velocity, which is refers to this equation. So based from equation 3.88, after we do the derivation of this equation, then we can get this equation, which is in terms of parabolic velocity. The maximum liquid velocity occurs at z is equals to 0. So uy maximum will be rho g del u over 2 mu, which is refers to equation 3.9, and the bulk average velocity of the liquid film is based from this equation, which is refers to uy. And if you refer to these two equations, the difference is the uy max is 2 mu, whereas the uy for the average, which is denoted as uy bar, is 3 mu. With no entrance effect, the film thickness for fully developed flow is independent of location y, and is we can say del is equals to this equation, where the tau is the liquid film flow rate per unit width of film, which is W. For the film flow, the Reynolds number, and we know that the Reynolds number is the ratio of the inertial force to the viscous force. This is the inertial force and this is the viscous force. And as for RH uy rho, and we know that the rho h, rho h is refers to equation hydraulic radius, which is equals to flow cross section over wet parameter is denoted as this direction. Then we substitute this equation into this equation, then we can get 4 rho uy rho. 4 del, because W del over W. So whenever we substitute rho h, which is equals to this equation, into the 3.93 equation, the rho h will be W del over W. So W over W will be 1. So the remaining will be 4 rho uy rho, 4 del uy rho over mu. And then we know that the tau, the tau is uy rho del. So then we can reduce this equation. Uy rho del will be the tau, so that's why the Reynolds number will be reduced to be 4 tau over mu, which is refers to equation 3.93. And Grimley states that when the Reynolds number is lesser than 8 until 25, depending on the surface tension and viscosity, flow in the film is laminar and the interface between the liquid film and gas is flat. The value of 25 obtained with water, when the application use is water. And for 8 to 25, the Reynolds number lesser than 8 to 25 and below 1200, the flow is still laminar, but only the ripples may appear at the interface unless suppressed by the addition of weighting agent. So meaning that when you calculate the Reynolds number and you get the Reynolds number is in between 25 until 1200, is still the condition is still in laminar flow, but maybe some of the ripples may appear at the interface of the wall. For flat interface and a low rate of mass transfer of A, which is refers to these two equations, okay, and the flow velocity profile is given for the previous equation, which is 3.89. We consider a mole balance of A for the incremental volume liquid film constant density as shown in figure previously. By neglecting the bulk flow of the Z direction and axial diffusion of Y direction, so we can conclude that the mass transfer of A from gas into liquid occur only by molecular diffusion, and we can do the assumption to be like this equation. By rearranging and simplifying the 3.94 equation, then we can get this simplified equation. And as we know that the limitation of Z whenever is approach 0, okay, and Y is approach 0, this equation will become this equation. Uy dCA over dy is equals to diffusivity coefficient del square Ca over del Z square. And by substituting the velocity profile, which is in the previous equation, these two previous equation, into 3.96, then we can get this equation, okay, 3.97. This PDE was solved. PDE is made of partial differential equation, was solved by this man, okay, and this man for the following boundaries condition. Still, this equation has its limitation, where the limitation is stated below, okay, which is Ca is equals to Cai at Z is equals to 0, and for Y is higher than 0, and concentration of A is equals to concentration of A at initial, okay, which is Y is equals to 0 when the Z is in between 0 and del. And the third one is dCA over dZ is equals to 0 whenever the Z is equals to del for the condition of Y in between 0 to L, where this L is the definition of L is the height of the vertical surface. The solution of this is in infinite series, where it gives the Ca as a function of Z and Y, okay, Z and Y, or of greater interest. If we want to use the higher values, we can use this relation, okay, which is refers to 3.98. For the condition of Y is equals to L, the result is this equation, okay, 3.99, where the N is equals to h over 3 over del over L multiplied with N PEM, and this is Schmidt number. So Schmidt number is equals to mu over rho dAB, where we know that it is equals to momentum diffusivity over the mass diffusivity, okay, mu over rho dAB. And NPEM is equals to N Reynolds number multiplied with the Schmidt number. Then we can get the Peclet number for mass transfer, where Peclet number is defined as this equation. Schmidt number is analog to Prandtl number, okay, which is refers to this equation, where Prandtl number is the momentum diffusivity over the thermal diffusivity, where the Peclet number of mass transfer is analog to the Peclet number for heat transfer, where the relation of Peclet number with the Prandtl number is Peclet number is equals to Reynolds number multiplied with Prandtl number. Then we will get this relation. Both are the ratio of convective to molecular transport, where the total rate of absorption A from gas into liquid film for height L and width Y is denoted as this relation. For the mass transfer coefficient, it is involved mass transfer coefficient with the heat transfer coefficient for latent Newton's law for cooling defined, which is defined as this equation, Q is equals to HA delta T, where Q is rate of heat transfer, A is the area of heat transfer, and delta T is the temperature of driving force. We will continue in the next section.